I'm Dr. Joshua Reichard, President of Omega Graduate School, and this is Statistics as a Language, Overview of Statistical Tests and Hypothesis Testing. The essential elements for this tutorial include basic types of statistical tests, hypothesis testing, critical values and p-values, sampling errors, power, types 1 and 2 errors, and performing and interpreting a test. What are statistical tests? Statistical tests help us make comparisons and identify relationships between variables in our data. Different tests are used for different purposes and under different conditions, and we have to know which test to use under which conditions. To determine what kind of test we need to use, there are particular questions we must ask. Number one, what are my hypotheses actually testing? In other words, what is it we're trying to actually determine by using statistics? Number two, what level of data does my instrument use? And we talked about the levels of data or levels of measurement in the previous tutorial, expressed as NOIR, nominal, ordinal, interval, and ratio data. Number three, are my data normally distributed? We also discussed normal distributions in the previous tutorial. Number four, what effect size is required for the test I am choosing? And number five, what is the minimum p-value required to reject a null hypothesis? And we will talk about power and effect and p-values in this tutorial. There are a few basic types of tests that we can use as tools in our tool belt for conducting dissertation research. These include analysis of variance, t-tests, goodness of fit, correlation, and linear regression. Analysis of variance, often called an ANOVA, asks the question, are the means of two or more samples different? So we take multiple samples and we want to know if the mean score on a particular measure is different between them. So I may collect a sample of churchgoers in one part of the state and another part of the state and another part of the state, and I want to know if their intrinsic religiosity is different between those samples. T-tests are similar, but they ask, are the means between two groups from the same sample different? So now I may say, I want to take one sample of all of the Baptists in a particular region, and I want to know, now splitting them male and female from the same sample, if their intrinsic religiosity is different between those groups from the same sample. The goodness of fit, this is typically a chi-square analysis, asks, do my data or my sample fit the expected data from the population? Goodness of fit is effectively asking whether or not our data can just be regarded as random chance or whether or not they have any predictable power to them. Correlation asks, what is the strength of relationship, if any, between two dependent variables? So I may take a sample and I want to know if there's a relationship between people's intrinsic religiosity and organizational religiosity. So in other words, does their church attendance, organizational religiosity, correlate with their intrinsic religiosity, how they apply their faith to their life? And so I may ask, if organizational religiosity is high, is intrinsic religiosity also high? And finally, linear regression asks, how well can we predict the value of a dependent variable on an independent variable? So this is about creating a model that helps us make predictions about how a dependent variable may perform in the future. We'll discuss all of these in much more detail in future tutorials, and we'll also touch on them throughout this tutorial. Before we get too deep into statistical tests, we need to talk about hypothesis testing. And in statistical testing, we use both a null and an alternate hypothesis. And these are expressed as H0, that's H with a little 0, and HA for the alternate hypothesis. And we do this because the burden of proof is on us. For example, a null hypothesis and alternate hypothesis might look like this. The null hypothesis would say there is no statistically significant difference in organizational religiosity scores between Baptists and Methodists in the given sample. The alternate hypothesis would read there is a statistically significant difference in organizational religiosity scores between Baptists and Methodists in the given sample. And effectively, our alternate hypothesis seems to be the intuitive one. That's the conjecture. That's the educated guess that we're making. But it's the null hypothesis that we actually have to test. The idea of using a null hypothesis may seem silly or unnecessary to you, but there actually is some good reason behind it. What we're doing with a null hypothesis is asking if our sample data actually represent the population for the given hypothesis, or if they only represent sampling errors. In other words, I have this sample, I've given them a survey, perhaps in our example, the Durrell instrument, and I've calculated organizational religiosity, and now I want to know whether or not the organizational religiosity between these two subgroups is actually representative of the entire population. So given we're conducting the research, the prevailing assumption is our hypothesis about the population is false. In other words, no one has demonstrated otherwise. So as of right now, there's no one who has suggested that there is a statistically significant difference in organizational religiosity between these two groups. The prevailing assumption is that our hypothesis about that population is false. It's up to us to reject the null hypothesis, not necessarily to prove the alternate hypothesis. But by rejecting the null hypothesis, we can accept the alternate hypothesis. The important thing to remember here is the burden of proof is on us. We're making a conjecture about people's behavior in social science research. We're making an educated guess with our hypothesis. And so what we actually have to do is reject that it's not the case in order to accept the alternate hypothesis that it is in fact the case. When we use statistical tests and test hypotheses, there are two things we need to take into consideration: critical values and the p-value. When we use a statistical test, critical values depend on the test, but generally are based on an alpha value of 0.05, which means the null hypothesis is rejected only 5% of the time when it's actually true. We can say then we have 95% accuracy. So this is pretty much the prevailing number for most statistical tests, a critical value of 95% accuracy. The p-value is the probability that the statistical test is true. A small p-value, generally less than 0.05, indicates that the null hypothesis is false. The smaller the p-value, the more confidence we can have in the rejection of the null hypothesis, meaning the closer to 100% accuracy we come on our critical value means that our p-value is shrinking. P-values are the simplest result in statistical testing, and as we get into conducting these statistical tests, you'll see that the software, and in the case of OGS we use Winx, the statistical tests will compute a p-value, and that p-value represents how statistically significant the results are. And by and large, if the test reports that p is less than 0.05, we can say that we reject the null hypothesis, and in so doing, the alternate hypothesis is accepted. We need to know in advance how small of a p-value is required to reject the test we're using. But by and large, it's generally p is less than 0.05. And for social science research, it would not be much smaller than that in any case. In things like clinical trials for pharmaceutical research, there might be a smaller p-value required or a greater critical value. That is, we may need 97 or 99% confidence every time we conduct a new test on a different sample. But for social science research, generally, p is less than 0.05 is adequate. And when we say p is less than 0.05, this is essentially the same as choosing a significance level, alpha, for a particular test. For example, we decide either to reject the null hypothesis if the test statistic exceeds the critical value, it is alpha at 0.05, or analogously to reject the null hypothesis if the p-value is smaller than 0.05. As I mentioned, most statistical software such as Winx report p-values rather than critical values, and all you really need to know is whether or not the p-value that's computed by a particular test is less than 0.05. And Winx will actually tell you whether or not the null hypothesis can be rejected based on the p-value that each statistical test computes. I would like to connect these concepts to the idea of statistics as a language, which is our tradition here at OGS. Whether or not we reject the null hypothesis at a particular alpha level, or p is less than 0.05, for example, is how we communicate with statistics, which again is the language of the scientific world. By simply rejecting or failing to reject a null hypothesis on this basis, and with an appropriate test, we can tell our audience something about the sample and hopefully about the population we're studying. We're actually communicating something meaningful about the population through our sampling and statistical testing and hypothesis testing that is meaningful to the rest of the world. When we report results, we're using statistics as a language. When we gather samples for research, we are again trying to represent the total population. And inevitably, when we collect samples, we can commit sample errors. By conducting research on a representative sample, we may encounter sample errors because the sample is not the whole population. We can try very hard to sample in a representative way, but ultimately we will always fall short because we cannot survey every single person in the entire population. Other errors that might occur when we're sampling include a poor sampling method. So how do we actually determine who should participate in the study? Problems with our survey or instrument, which will obviously skew the results if our questions are poorly worded or our instrument is not validated, or behavioral effects, which skew the data for participants in the sample. So was there undue influence on the participants? How was the location where the survey was conducted? Were they distracted? And so on and so forth. But generally, we can say that the larger the sample size, and we call sample size in statistics n, the more accurately it represents the population. And so if we get a larger sample that's more representative of the population, we can have more confidence in our results. In social science research, it's tempting to rely on p-values alone, especially because the statistical software will compute p-values so easily. But p-values do not tell the whole story. We also have to consider effect size. Effect size is a simple way of quantifying the difference between two groups that has many advantages over the use of tests of statistical significance, that is, p-values alone. Effect size emphasizes the size of the difference regardless of the sample size. And the statistician Cohen came up with a value called D to represent effect size. And Cohen said this, that D of 0.2 is considered a small effect size, a D of 0.5 is a medium effect size, and a D of 0.8 is a large effect size. So what this means is that if two groups' means don't differ by 0.2 standard deviations or more, the difference is trivial, even if it is statistically significant. So we might get a p-value that tells us that it's statistically significant, but if the effect size is not greater than 0.2 standard deviations or more, that is Cohen's D, then we have to question the results. So combining p-values and effect size give us a much more holistic picture of whether or not the hypothesis that the null hypothesis we've rejected is meaningful. We also need to consider statistical power. Power is the probability that a test rejects the null hypothesis when the alternate hypothesis is true. Generally, power is specified at 0.80 or 80% probability. That means it's accurate 80% of the time, that a test will yield a statistically significant effect if it's actually there. So in other words, if we know that there is a statistically significant effect in the question we're asking, in the hypothesis we're posing, the null hypothesis we're testing, we need to know that 80% of the time it's going to find that effect and find a statistically significant p-value less than 0.05 if it's actually there. This means we have an 80% chance of ending up with a p-value of less than 0.05, and that is 95% confidence in a statistical test. Power is the statistical muscle of being able to detect effects in your sample if they are truly there and truly representative of the population. So you can try to remember that in terms of power and muscle. And Winks will report the power of a particular statistical test. Aside from sampling errors, there are two other types of errors that can occur in statistical tests, type 1 and type 2 errors. Type 1, a false positive occurs when we incorrectly reject a true null hypothesis. Your findings occurred by chance. Type 2, a false negative occurs when we fail to reject a null hypothesis when it is really false. Your findings are significant, but you think they occurred by chance. We want to try to minimize both of these types of errors, but they are inversely proportional. That is, decreasing a type 1 error rate increases a type 2 error rate, and vice versa. There are some practical ways we can mitigate these errors of getting these false positives and false negatives. First, we can minimize the risk for a type 1 error by using a lower value for p. And we can minimize a type 2 error by increasing our sample size. So in other words, if we want to try to lower the type 1 error, we may have to make p even less than 0.05. So maybe p would be less than 0.01, and that would help us mitigate the risk of a type 1 error. A type 2 error can be mitigated by increasing sample size. Now that we've discussed some of the fundamentals of statistical testing, let's talk about the practical steps of performing and interpreting a statistical test. Number 1, state a null hypothesis and usually an alternate hypothesis. And if those are well written and clear, then we know exactly what we need to test, and we should know which test we need to use. Number 2, test the hypothesis using the right statistical test. And of course, we mean there the null hypothesis. And number 3, interpret the test and make a decision using a decision criterion, usually the p-value, based on the assumption the null hypothesis has been satisfied. Typically, the reported p-value is the most convenient way to decide on statistical significance. For most cases, if the p-value is less than 0.05, you reject the null hypothesis in favor of the alternate hypothesis. At the beginning of this tutorial, we introduced some of the basic types of tests. Let's just review those again. Analysis of variance is for comparing the means of 2 or more samples. T-tests are for comparing the means between 2 groups from the same sample. Goodness of fit is to see whether or not the sample data fit the expected data of the population. Correlation is to determine the strength of relationship between any 2 dependent variables. And a linear regression is for predicting the value of a dependent variable on the basis of an independent variable. In the previous tutorial, we briefly touched on the idea of parametric and nonparametric tests in the context of normal distributions. Nonparametric tests are useful as an alternative to parametric tests when you suspect that the data are not normal or that variances between groups are unequal. And Winks has the ability to compute whether or not your sample data are normally distributed. And you can use that calculation to determine which kind of test you need to use for which purpose. So independent group t-tests, one-way ANOVA, paired t-tests, repeated measures ANOVA are all significant difference tests. And each one of them has their non-parametric equivalents if your data are not normally distributed. So that's the Mann-Whitney-U, the Kruskal-Wallis, the Wilcox-Signed rank, and the Friedman's ANOVA. And by and large, unless you have a very large sample size, you're going to end up using non-parametric tests in your dissertation research. Then if you're doing a correlational study, Pearson's product moment of correlation is the parametric test, and Spearman's rank correlation coefficient is the non-parametric equivalent. The chi-square, which is the goodness of fit test, stands on its own, and that's used primarily for nominal data. At the beginning of this tutorial, we reviewed some of the questions we have to ask when choosing a statistical test, and let's review those again. Number 1, what are my hypotheses actually testing? Number 2, which level of data does my instrument use? Nominal, ordinal, interval, or ratio data? Number 3, are my data normally distributed? Number 4, what effect size is required for the test I'm choosing? And number 5, what is the minimum p-value required to reject a null hypothesis? And by and large, that's going to be p is less than 0.05. Well, we've covered a lot of concepts in this tutorial, so I'd like to pause for a knowledge check. Let's reflect on these questions. Number 1, why is a null hypothesis important? Why is the burden of proof on the researcher? Number 2, how are type 1 and type 2 errors related? How can they each be minimized? Number 3, why is power important in sampling? Number 4, what does the p-value tell us? How does it inform hypothesis testing? Number 5, why does effect size help us paint a more holistic picture of our data? And number 6, how do we choose between parametric and non-parametric procedures?